Voice all mute, mute all. And share screen. Share. First of all, there is a midterm survey in Canvas, so please take a look and participate in the survey so that we'll get some ideas about how to improve this course in the future. Okay, this week we will be considering basically two different approaches to measure human beings' happiness or welfare, okay? The other day, I think I talked about the happiness measure. Some European countries seem to be the happiest in the world among all nations. But we will be using utility index, which is different from happiness index, I suppose. Happiness index may be related to consumption. Say utility is a function of consumption goods, not just one good, any consumption goods, all of those consumption goods, say X. This is a vector of goods like good 1, good 2, good 3, etc. Okay? But it also depends on the social norm. Even if your income doubles, if everybody else's income doubles, then you should feel happier, but many people don't feel the same way. They have this idea of keeping up with the Joneses. So if, of course, if no one has a new car and you just bought a new car, you would feel much happier. But when the neighbor buys another car, when you don't, then you like to follow suit. In such a case, envy plays a role in consumer demand, okay? So instead of being content with what one consumes, you're looking at the consumption bundle of other people, neighbors, neighboring nations, etc. So in this case, even if you double their income, the population may not be exactly happy when other nations also double their income, okay? So envy plays a role in consumer demand functions. But we're going to assume that in this course, we're going to assume that envy does not play a role, okay? So one's utility is solely based on one's own consumption of goods. Let me see whether there's a problem. Any questions so far? Okay, so instead of assuming that envy plays a role, we'll assume that one's welfare solely depends on his own consumption, not someone else's consumption, okay? And that's called the utility function. So one's happiness, if we were using happiness, the word happiness, this utility function measures happiness or welfare, but it solely depends on his own consumption, not someone else's consumption bundle, okay? There have been two different approaches. And the textbook doesn't, the textbook mentions both, but it does not give names to those. So I'll give the names, okay? One is called cardinal utility. Some classical economists like Jeremy Bentham thought utility is measurable in the cardinal sense. What is cardinal utility? It means that like money income is a cardinal measure. If you if everybody else is earning $100 an hour, and if you earn $200 an hour, well, then the statement that you're earning twice as much as the next person, that statement makes economic sense. But you cannot say between two ladies, Jane is 100% more beautiful than Nancy, or vice versa. That makes no sense, okay? So in that case, beauty is not a cardinal measure. You can compare beauty of two individuals and say one is better looking than the other, but it does not make sense to say that one is 100% better looking than the other. Some people say jokingly that, but that has no economic or social meaning, okay? But in the old days, Jeremy Bentham, for instance, thought that utility is cardinally measurable. And we're going to illustrate this case using the water and diamond paradox later. A second group was more the new group of economists thought that utility is measurable in the ordinal sense. So instead of saying one is 100%, 50% smarter than the other person, that makes no sense. You could say one is smarter than person A is better than, is smarter than person B, etc. That makes sense. That makes economic sense or social sense. So if that is the case, we call it smartness would be an ordinal index, okay? So if utility is measurable in a cardinal sense, that's called cardinal utility, and it's going to look like this. Consumption of X is measured on this axis, consumption of Y on that axis, and welfare level or utility level is measured on the vertical axis, okay? So you can hold one good constant and then increase the amount of the other good and see how this utility function goes up. This rate of change in utility for a small change in Y is called the marginal utility of Y. And likewise, the change, the increment in utility for a small change in consumption of X, that's called the marginal utility, okay? So marginal utility is a cardinal concept. Marginal utility makes sense to only cardinal utility functions, okay? So I just explained the marginal utility, right? As consumption of X increases, utility level is going up, delta U is positive, and this increment, the rate of change in this, the rate of change or increment in utility for a small change in consumption of X is called the marginal utility of that good. And in this part of this course, we'll say that marginal utility is always positive, meaning more is better. And I mentioned, I cited an example of the owner of Amazon company, Bezos. He's a centibillionaire. His worth is about $188 billion, right? That's supposed to be, he's supposed to be the wealthiest person on the planet. Okay. Did he ever say, "Dear Lord, I'm blessed, I'm happy, I have enough. Don't shower me with more money"? No, we did not hear such a person. Nobody's counting their blessings. Okay, so we are going to argue. I'm sure there are some small number of people who are saying, even if they eat only 2 meals a day, "Oh dear Lord, I'm happy. Thank you so much. Don't shower. Don't give me more money." I'm sure there are some religious people like that, especially among the Buddhists or Christians. Okay, but in this part of the theory, we're going to assume this utility mountain is always rising, okay, never reaches a peak. There is no peak. That's the assumption, okay? This is a cardinal utility function. There is no peak. There is no peak. It's not very easy to write letters with the mouse. There is no peak in the utility function, okay? And this is a picture of a shopping mall in the western part of Berlin. West Berlin is much brighter than East Berlin, similar to the satellite map at night, like between North Korea and South Korea. North Korea is very, very dark. They don't have electricity, not much, maybe supplied only 1 hour per day. Whereas South Korea has lots of electricity, so their shopping malls are glitzy, and all. West Berlin likewise, uh, very, very bright and sparkling and so on. More is better. That's the idea. That's the Western people's idea, okay? More is better. Work hard. Everything you have to earn, you have to work for it, you have to earn it. Despite the labor and the opportunity cost, more is better, okay? So everybody's working very hard. Now, for the cardinal utility function, this notion is critical, diminishing marginal utility. So that means as you consume more, marginal utility is positive and total utility is going up, but the increment in utility, marginal utility is shrinking and shrinking as you consume more. So when you have when your income is close to $1 billion, marginal utility of another buck is negligible. But still it is positive, okay? That's the idea, diminishing marginal utility. But some people sometimes go overboard and drink too much, and then there are consequences, as shown in this picture. Beyond a certain level, marginal utility becomes negative. In reality, I'm talking about in practice. If you consume something too much, well, there will be consequences, negative consequences like this. Okay, so what is the diamond and water paradox? Okay, this paradox is illustrated by this cardinal utility. That's a special case of cardinal utility is additive utility function. So to illustrate, what is the meaning of the paradox? Well, water is infinitely more useful than diamonds. Diamonds are useful for showing off for some really rich people and to cut hard materials like steel and titanium and so on. Diamond is the strongest material on the planet. So diamond blades are used to cut hard materials like concrete and other things. But water, you cannot survive without water. So in the desert, you offer two things. Hey, here is a Hope diamond that's worth billions of dollars, and water. Well, obviously, you have very little use of diamonds. You will be reaching for a bottle of water so that you could extend your life one more hour, maybe one more day, 2 more days until rescue comes. So water is infinitely more useful than diamonds, but how come the price of water is so low compared to that of diamonds? That was a paradox, okay? How do you explain this? A thirsty man in the desert, there is no question about it. You're thirsty, you gotta drink, and you would trade very expensive diamonds for a few bottles of water, okay? Your utility from diamonds are practically zero in such a drastic environment of deserts. So this has been called the diamond water paradox, okay? So how do you explain that? A special case of cardinal utility function is additive utility function, okay? This is, in general, this is not true, but we'll consider a special case. So your utility depends on the consumption of diamonds, U of D, and your consumption, utility of, say, utility of water, etc. Okay, so if you're consuming three different goods, you have thermometers measuring your welfare or happiness. And with additive utility function, marginal utility solely depends on its quantity. Marginal utility of water does not depend on how many diamond rings do you have, okay? That's the assumption, okay? Although that's not necessary, but that is the assumption. So let me illustrate. Marginal utility of water is your demand curve. Marginal utility of water is down sloping like that. This is your demand for water, okay? So what happens if price of water falls that much? Well, this is how much water you're going to drink, okay? So demand for water is simply marginal utility of water. What about demand for diamonds? Well, here's demand for diamonds. Demand for diamonds, D is your marginal utility of diamonds. Supply of diamond in the world market is very, very limited. So you equate marginal utility of diamonds to price of diamonds right there. That is your demand. Whereas supply of water is abundant, well, maybe not anymore. Maybe not by the end of this century. There will be so much scarcity. Water will be so scarce that water price may be very high. But for now, at present, or at least for the next decade, water supply is abundant, water price is very low, so we're consuming that much water, okay? So it's quite possible, even though water may be infinitely more useful than diamonds, price is not equated to total utility. Price is not equated to total utility, okay? Price is consumers maximize utility. How? Demand for water intersects price of water right there. That's how quantity of water demanded is determined, okay? Quantity of diamonds, well, that occurs right here. At this price, demand for water and supply water are the same, and the market for diamonds clear, okay? So this explains why water is infinitely more, 10,000 times more useful than diamonds. Still, price of water would be very, very low, much lower than that of diamonds, okay? So there is no paradox here. Price that we pay is not related to total utility, but marginal utility. Okay, so that explains the water and diamond paradox. So here is a picture of vending machine in Kyoto, Japan. That's an old city that was built in the 8th century AD. And there is a lot of vending machines in Japan, more so than in the United States. We don't have that many vending machines in the United States. Vending machines are very popular in Japan. So when you compare all, well, their price is about the same. Well, maybe some are cheaper than others. So you are weighing marginal utility and price. So let me use the transparencies prepared by other professors. Is this a happy man? It was difficult to figure out what this was about. Obviously, given a short period of time, this guy is trying to finish. This must have been our eating contest. How many hot dogs can you chow down in 10 minutes or something like that? So people are competing, but the more sausages or hot dogs you eat, at first you're hungry, you will be happy, but as you consume more and more, gradually you become satiated, and an extra hot dog gives you displeasure rather than pleasure. Eventually, oops, let me use common. Marginal, oops. Marginal utility of hot dog becomes negative, okay? Given a limited amount of time, if you try to chow down so many hot dogs, eventually there comes a point where marginal utility of hot dogs become negative, okay? So there is a law of diminishing marginal utility. Beyond a certain point, marginal utility of a consumption good becomes negative. So instead of becoming a good, satisfying your needs, it becomes a bad, okay? When marginal utility of a good is negative, instead of being a good, it becomes a bad. like garbage. We have too much. All this plastic garbage is produced by China, Japan, and Asian countries. They pile up through all this swirling uh, swirling tides. Eventually, they accumulate themselves in the center of Pacific Ocean, I hear. So principle of diminishing marginal utility is similar to the principle of diminishing marginal returns in production. We'll study about that later, okay? So what is the equilibrium condition? When you're given a cardinal utility function, how do you maximize utility? What is the right combination of consumption goods? Well, here's the rule. Marginal utility, if there are two goods, A and B, your choice of A and B must be such that marginal utility of A divided by price of A must be equal to marginal utility of B divided by price of B. What is the meaning of this? Marginal utility of, listen carefully, okay? Watch me closely. Marginal utility of good A divided by price of A. That is practically marginal utility per dollar. So if your marginal utility is 20 units and price of this good is $2, then marginal utility per dollar spent on good A is 10 utils. Okay, that must be the same as that marginal utility of per dollar spent on good B. When these are all equalized, for every consumption good you purchase, marginal utility per dollar is equalized, then you have maximized utility. What happens if that's not the case? So this is the second case. What if marginal utility of good A per divided by price of A, that's marginal utility of $1. Marginal utility per dollar is higher in good A than that in good B. Then right here, pay close attention right here. You don't get enough bang for your buck. You have more bang for the buck right there. So you should withdraw $1 and put it over there. Okay, as you withdraw $1 from B, marginal utility of B goes up. Whereas as you spend more money on good A, marginal utility, because of the principle of diminishing marginal utility is going down. Okay, so you can achieve balance between the two. So when marginal utility of dollars spent on good A is equalized, when marginal utility per dollar spent on each good is equalized, when this becomes equalized, you have reached utility maximization. You have achieved maximum utility, okay? As when this was heavier, you're getting more bang for the buck. You should spend more money right there. Pour more money here. If the government has two different departments and you don't get much output here, well, you need to withdraw, defund that portion and increase funding over there, okay? Until you have reached the balance between the two. Why does the demand curve slope down? Well, using cardinal utility function, I think I showed it a minute ago. Well, okay, let's go back. So when marginal utility per dollar of expenditure is equalized across all goods, you have reached maximum utility, okay? Why is the demand curve negatively sloped? Because as we have shown, marginal utility of water is the water demand curve. Marginal utility of diamonds is his demand curve for diamonds. And because of the diminishing marginal utility, demand curve is negatively sloped. They're the same thing. Marginal utility curve and demand curve, they mean the same thing with additive utility function, okay? Now, the chapter also talks about income and substitution effects, and this comes from ordinal approach. Ordinal utility function, okay? This does not come from the cardinal utility function. So we will consider this approach. May not be able to finish it today, but we'll give you, we will lay the basis for ordinal approach. This ordinal approach, some economists thought that, yeah, cardinal utility function explains the water and diamond paradox, but maybe that is like using a hammer to smash a mosquito. You don't, or using an atomic bomb to smash a mosquito, okay? So using Occam's razor, right? I think we studied about Occam's razor at the beginning of the semester. Cardinal utility is too much. Why don't we simplify it? Well, maybe we don't need to impose such a restrictive assumption. So they were saying that the modern economists were beginning to argue, well, consumers have ordinal utility function. In other words, the consumer can rank which is better. Is this better than the other? Instead of saying one bundle is 50% better than the other bundle, okay? So that's called the ordinal utility approach. And so with this ordinal utility function, what are we trying to do? So if there are two goods, X is measured, quantity of X is measured on the horizontal axis. Quantity of the other good, say Y, is measured on Y axis. And the vertical axis measures total utility, okay? Total utility. Now, at certain height, you slice this utility function and at the same height, then you're going to generate a contour like this. These are called indifference curves, okay? That is the locus of consumption of X and Y that yield the same utility level, okay? Of course, if you have a horizontal slice at the higher level, say this another level, higher level of welfare, you're going to generate another contour. This contour, that contour, and so on, okay? These are called indifference curves. And then we can assume consumers are rational, okay? We're always going to invoke that assumption. So there are similar notions in our daily lives that are similar. I mean, that are similar to indifference curves. For instance, if you look at the weather map, although it is not visible to naked eye, some places air pressure is the lowest here. Lowest here, that's the bottom. Here, say here, this is isobaric map. Iso mean equal, isobar map. So when you see weather forecast, you're watching this kind of isobar map. Iso means equal, so that notion is similar to indifference curves, okay? So this is the lowest point, L. L stands for low, okay? 998. Air pressure is only 998. Then it rises to 1,000, then to 1,004, 1,008, etc. Here's another lowest point, 953. It goes up. And this circle, well, it's not a perfect circle, but it looks like ellipse. But at any rate, along that contour, air pressure remains the same, okay? And then it goes up to 972, 980, 1,000, and so on. And around here, it keeps rising, but there is a different center. There are different centers of high air pressure. So it goes up this way, all the way to highest point where air pressure reaches its maximum, 1,025. At that point, weather is very nice. No tornado, no hurricane. Low pressure means precipitation. Lots of rain or snow or things like that would happen, okay? So this isobar contour is very similar in terms of concept. There is a conceptual similarity between these two, isobar map and indifference curves. Indifference curves is a locus of consumption bundles that yield the same level of utility. And they have 4 characteristics. Indifference curves are all negatively sloped. Why not? Why not positively sloped? Well, sometimes it is positively sloped, like the guy who was eating so many hot dogs, he was almost throwing up, okay? So when when a commodity when a good turns into a bad, indifference curve becomes positively sloped, okay? When one of those goods one of those two goods turns into a bad, then the indifference curves will become positively sloped. But we have ruled this out. Okay, even Bezos says, give me more, I'll be happier. If you fork over $100 more, I'll be happier. Okay, that's the assumption, okay? I'm not implying that he's a bad person. I'm just talking about human desires. Secondly, indifference curves are non-intersecting. Oh, by the way, this cardinal approach is well explained in the textbook. Indifference curve analysis is mentioned as a as a as an extra, so this will not be tested on the exam. Okay, indifference curve analysis will not be included in the midterm or final exam. This is an extra. Okay. Secondly, indifference curves are non-intersecting. They never intersect each other. Okay. Well, if they intersect each other, then we run into logical inconsistency. For instance, suppose A and C lie on the same indifference curve, and A and B lie on another indifference curve, say I prime I. Well, then B is indifferent to A because they lie on the same indifference curve, and A and C lie on the same indifference curve, so B and C must be indifferent. Well, that is not possible because bundle C has more of every good than bundle B, okay? So that's a logical inconsistency. So this diagram shows indifference curves are not intersecting. They cannot intersect each other. Okay. Third characteristic, a higher indifference curve always represents a higher utility level because this utility mountain does not have a peak. So you can always reach a higher, and higher and higher indifference curve. Never reaches a peak. There is no peak in this indifference map. Okay, and finally, all these indifference curves are convex to the origin. All these indifference curves are convex to the origin like this. Okay, what is the meaning of this? Well, that means consumers want balanced consumption bundle. A little bit of this, a little bit of that, instead of going all in. I only want good A. If you have a concave indifference curves like this, then they either want either this good or that good, but not both. A little bit of this, a little bit of that is no good. And sometimes this happens when you take medicine. They say, oh, you have a problem with COVID virus? Okay, take this medicine or the other medicine, but not both. Sometimes they interact chemically each other. They interact and produce toxins in human bodies, human biomechanism, and sometimes consumption of both is not recommended in certain cases. Okay, so ruling out these special cases, we want to rule out those cases. Okay, indifference curves are convex to the origin, not this kind, not this kind, but this kind. Indifference curves are convex to the origin. So given budget constraints, consumers want some of this good, some of that good. Okay, instead of, no, I only want potato chips. I don't want to, I don't want to eat rice or bread, or I just want potato chips. That shows kind of addiction. Like some crazy people keep drinking, I only want Scotch whiskey. One shot, two shots. Well, are you hungry? No, I'm not hungry. I keep drinking the same liquor or eat the same food. Uh, I hear some people lived on McDonald's hamburger for a month, every day eating the same hamburger and still survive. But at any rate, that shows the addictive behavior. When you show addiction, addiction, you have concave indifference curves. So you only specialize in one consumption good, consume only one good, because as you increase consumption, become more addicted, you keep asking for more and more. How about, aren't you thirsty? No. Aren't you hungry? No. That shows addictive behavior, okay? So barring this addictive case, or barring the case of habit formation, like uh, all these drugs, uh, we assume rational consumers have convex indifference curves. Okay? All right, we'll stop here. Any questions? All right, well, that's the end of it today.